You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that had, has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you. You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcasts, and I have Elizabeth Parrish, CEO of BioViva. It's a company committed to extending healthy lifespans using cell technologies. And Liz wears many hats: humanitarian, entrepreneur, innovator, podcaster, and a leading voice for genetic cures. And we're going to get into why and how. So, Elizabeth, thanks for coming.
Yeah, thanks for having me on Future Tech. It's great to talk to you again.
Yeah, so, it's okay to have a recap, but what's your whole motivation for wanting to be in the space of, medicine and specifically looking for genetic cures to various problems?
All right, so what got me started in this area in a brief way as I can possibly say is, my son was diagnosed with type 1 diabetes after I had done 2 years of area research in the area of stem cells. And so I had been working in the regenerative medicine area trying to vet out, what were the caveats, whether the technology was working, whether it was not working, and how to get education out there so we could get funding through to this vital technology. And when my son was diagnosed, I noticed that there was no translation of regenerative medicine in 2 children in high need, that while I was in the hospital, there were other kids there that were dying of diseases. And I realized that in medicine, what we do is we essentially treat symptoms. We have a sick care system instead of a healthcare system. We're not translating therapeutics through to patients fast enough to save their lives. It appears that bioethically, we think that patients should rather die than take part in experimental medicine, and I really rally against that 100%. So I went and tried to learn about more uses of regenerative medicine, specifically in genetics, because I had felt for a couple of years working in stem cells that essentially the mechanisms of the epigenetics in the cells, that the genes themselves were responsible for the regeneration, and that if we could have that sort of outcome in a patient's body without having to apply stem cells, we would have a much better outcome. So I started looking at genetics. Ran into a SINS conference, Aubrey de Grey's group, met with a bunch of geneticists and specialists in the area, asked them how this technology of aging could be translated to childhood disease because that was my focus target to cure. And it turns out that regenerative medicine and the aspects of using gene and cell therapy, still stem cells as well, will actually create a lot of cures for a lot of childhood diseases while we tackle the biggest unmet need, which is biological aging. By treating biological aging, we can change the outcome of diseases that are preventable like Alzheimer's, cancer, heart disease, organ failure like kidney disease, and essentially then bring those cures back to kids and then create a life for kids where they don't just get healthy for a couple decades only to become sick again with the diseases that we vastly die of. So that is it in a nutshell, and I hope that made sense.
Yeah, it's just, there's, what I want to ask you is there's many conditions out there, and then there's mechanisms. So maybe first, what are the particular conditions that you want to address first? Because, no one can really do them all. So is it
right.
type 1 diabetes in children, or what is it?
So essentially, type 1 diabetes is an autoimmune disease. There are a couple of really great cell type technologies where they take the beta cells from the patients and put them into the liver or put them into capsules that the immune system cannot target. The cure for it, though, will vastly be in affecting genetics. We're not there yet. It's called a complex disorder. Where we're at in treating complex disorder is more on the lines of treating aging with regenerative type therapies, which those kids will need as well. So when we look at biological aging, we're looking at the hallmarks of aging. And you're right, not one treatment is going to treat the hallmarks of aging. So we have a platform, it's called Integrative Health Systems, that essentially gives people access to a myriad of different types of regenerative gene therapies that they can participate in to help find the gene therapies that work in certain aspects of the hallmarks of aging and then work those back into treating a multi-combinatorial gene therapy that will treat disease. But each one of the gene therapies we look at treats a childhood disease. So if you're wondering where these would work, so when you're looking at a regenerative therapy, we're talking about creating one treatment that affects all of the diseases of aging. And each one of the treatments we look at actually also has an effect of treating a childhood disease. So one of the gene therapies we look at is telomerase induction. So the telomeres are the caps at the ends of your chromosomes, and they shorten with each cellular division. One of the treatments for aging will have to be dealing with this problem of cellular senescence and cell proliferation. So you need long telomeres or else the cells stop dividing. So that treats biological aging, that if we can keep the telomeres long, we'll very likely keep a healthier epigenetic state in the cell and avoid things like cancers and other diseases like cardiovascular disease and Alzheimer's that are associated with short telomeres. But we can also treat a childhood disease called progeria. That is, the hallmark of that disease is the attrition of telomeres. These kids die in their teens, very young, of all of the same diseases that we die of at much older ages. So it's considered accelerated aging. Another gene therapy we look at is one that increases muscle mass. So in clinical trials, about 8 out of 10 patients have their muscle mass increased in muscular dystrophy states. We're using it for an aging population, but you can see how driving the cost down by treating one of the biggest unmet needs, the whole population, with something like a muscle enhancer, therefore keeping their body strong and making it so they don't die from falls associated with frailty, which I just said at the bedside as someone who died that way last week. By treating the biggest unmet need, we create a really affordable therapy that can also treat muscular disorders, myopathies in young children. And it just goes on one after another with the gene therapies that we're looking at right now. We're looking at 4 different gene therapies. We will expand that as we go. George Church, one of our scientific advisors, who's a professor of genetics at Harvard, just came out with his list of 45 genes associated with treating aging. And some of them we will actually pull and start looking at for specificity as well. But all of them that we target will also treat childhood disease as well.
Yeah, I would think just initially, if you want to study aging, look at old people, not children. And I know that you want to help children because, that population is near and dear to your heart and many people's hearts, obviously, that either have or don't have children. Do you think that in terms of the study of aging and how to slow aging or reverse it or stop it, where is the most useful information to be had? Is it in studying children, or is it in studying old people, or where do you think the best learnings will come from there?
So the best learning will come from the biggest cohort, and that will be aging adults. This is the biggest, fastest way to get there. As far as where you would glean the most information right now, it's in the meta-analysis of research that has already happened. That's where you would have to go to right now. What we're doing is we're starting to get the first human data on how these gene therapies perform in humans, because it's, one human outweighs 1,000 mouse studies, and two, it just becomes exponentially more relevant. And so right now, the platform company that we work with, Integrative Health Systems, which we hope will become an accepted, tested system for biotechnology in general. We hope it's the first place investors take companies that they're interested in, that they think are ready for human studies, to find out how drugs work in humans before they start to raise $1 billion for the regulatory service. That system right now for us, we're preparing to handle the data, but they already have many patients who have taken regenerative gene therapies, and then the bioinformatics platform of BioViva is going to be handling that data and assessing, how these patients are doing, how the drugs are performing, the safety, and trying to glean some amount of efficacy and low numbers as those numbers grow. I am no longer the only patient with a dual gene therapy. There are several patients now that through that platform who have taken that, and we're really excited about handling their data.
So you said, okay, you've had dual gene therapy. What have you had done to yourself, and what were the effects that you noticed?
Oh, right. So, yeah, we should probably, for listeners, go back a little bit. So when I started BioViva, I started it in 2015, and the whole idea of BioViva was to get human data on how well these drugs performed. So stepping forward as the CEO of the company, I took the first 2 gene therapies to treat biological aging. One of them was the myostatin inhibitor, the gene therapy that increases muscle mass in Duchenne's muscular dystrophy. So I was not a first in use for that, but I was a first in use concept for aging for the company. And the second one was the telomerase inducer, which had not been used in vivo, meaning in a body, in a human. It had been used in human cells. It had been used for over a decade in animal studies. It had reversed biological aging in gene knockout mice, and it had lengthened the healthy lifespan of aged mice. So we were really excited about that. We're now doing another study in BioViva for telomerase induction in mice with our new viral vector delivery. So we'll be doing a longevity study now. The mice have just showed up to the university, and they're going through their quarantine now, and we're about to start. So we're also doing a separate test for the myostatin inhibitor in those mice as a longevity study as well. So we're doing a new delivery for that.
Quick question here. Yeah, quick question. So what is a myostatin inhibitor, and what is the telomerase inductor? What are those things for people?
Yeah, so that's a really good question, and especially when we don't have visuals, when people are just listening, I'm going to try to make this as explicit as possible, because a myostatin inhibitor, like a lot of people just tune out. They're like, what is that? Like, just stop. I don't even know what words you just said. So a myostatin is a protein in your blood that regulates muscle growth. So when you're young and you have a lot of growth hormone, it keeps your body from expending a bunch of energy creating huge muscles that might not be great for your metabolic state, meaning maybe you don't have enough nutrition for all these muscles. So it's a regulator to muscle growth. As you age, that regulator, it becomes counterproductive. We start to lose muscle mass at percentages after the age of 30, 35, depending on the person, and it becomes detrimental. Frailty is a real issue with the aging, falls, broken hips, not being able to climb stairs, walkers. You've seen that. That's called palliative care, when we start throwing devices at people because they don't have the strength anymore to hold themselves up. That's called sarcopenia. There's another condition called cachexia that happens after cancer treatments, and it's also muscle wasting associated with chemotherapy. So muscle wasting happens, and because of myostatin in your blood inhibiting muscle growth, it becomes detrimental. So a myostatin inhibitor, you can imagine inhibitor means to stop something. It actually blocks myostatin's action of performance. Not 100%. That's why with the gene therapy we don't see people looking like the Incredible Hulk. But what happens is we titrate, meaning we decide the amount of dose that a person needs to take to gain muscle mass. So a myostatin inhibitor is, in the case of gene therapy, is a gene that creates a protein that you can imagine goes out in the blood. It finds myostatin and it binds to it so that it cannot regulate your muscle growth anymore in the way that it did. And again, we don't get incredibly huge bodies from doing this. We get, 10, 20% muscle mass gain from the type of therapeutic doses that are given. And so that's what that is. Did that make sense?
Yeah, it makes sense. Why did you have this therapy done? Were you experiencing muscle wasting, and were you ripped afterwards, or what did you experience? People always like to hear personal stories.
Right. So what sort of outcome would you get from this? So when I did it, because I was experiencing muscle loss, I was in my 40s when I did the gene therapy. I was 44, and what happened is what we expect to see happen. Actually, I had been exercising a lot before I did the gene therapy. And after I did the gene therapy, I was on some immune suppression, so I wasn't doing a lot of exercising. And then it just so turned out that the information was leaked out of the company that we had treated the first patient. And at that point, I was on a lot of airplanes, not exercising regularly, and still we saw muscle mass increase. We not only saw that, we do MRI images before and after. We saw a decrease in white fat, which we would expect with muscle mass increase. The fat between the muscles also decreased. We saw an increase in insulin sensitivity. So the reason that you would do a gene therapy like this is not just for muscle mass loss, it's also for what we call metabolic disorder, or things that lead to type 2 diabetes that are aging associated. So when you increase muscle mass, you increase insulin sensitivity and you decrease white fat. And we believe that that will be a great protection for type 2 diabetes. I did not have type 2 diabetes, and I did not have clinical sarcopenia. I simply think that an aging body needs to be treated as soon as possible before you're diagnosed with those diseases, or soon after, if you can be. We also are looking to treat vastly super aging people. We're putting up a campaign. It's called Help Them See the Future through Maximum Life Foundation. And we are very interested in treating a very old population, but I believe that these gene therapies will be worked back as preventative medicine in the future. Patients rather using them before they get sick, rather than waiting to get sick. The second thing that we talked... Mm-hmm.
One quick question. When you did the myostatin inhibitor,
Mm-hmm.
You experienced a lot of benefits, but you said you had to have your immune system suppressed. Why is that?
Oh, so for a gene therapy, you temporarily have your immune system suppressed around the gene therapy, and for a few weeks after the gene therapy, you come off of the immune suppression slowly. So the reason that you do that is so the uptake of the gene therapy is the best possible. You don't want to have a reaction to the gene therapy. You want to give the gene therapy time to work. You don't want your immune system scavenging out the therapeutic. And so it's not a huge immune suppression at all. It's a light immune suppression, but it does affect your immune system. You basically, it has effects on you that, you probably won't be doing a lot of exercising during that time. You're trying to lay low. You're not exposing yourself to a lot of contaminants. So it definitely disrupted my regular exercise pattern for a few weeks.
But it's no different than, I guess, if you're on chemo. From what I've heard, the patients have to do the same thing. Unfortunately, isolate themselves.
Yeah, it's less so than if you're on chemo. That's much more serious. Our immune suppression is a little bit more like if you're somebody who had a severe allergy and you went to the doctor and you would take a 2-week long treatment of immune suppression. It's not something that would actually make you, deathly ill if you were exposed to some minor infection. So yeah, it's nothing that severe. I should probably make that clear. And I'm not trying to be appealing to people at all. I'm just telling you the truth. It's not you're not going to be going through some severe process to go through a gene therapy.
Oh, that's good. And then you
I think I still need
telomerase,
to explain the telomerase inducer. Do you want me to do that?
I was just about to ask you. I was going to say, then you were, and you did your telomerase induction. So what was the reason for that? What was what did it do to you, et cetera? Tell me about that.
Right. So why would you do a telomerase inducer? Well, short telomeres are correlated with all of the diseases of aging. They're associated with some childhood diseases as well. We know that critically short telomeres are generally always found around the point of diagnosis. We know that telomere length is associated with healthy cell division. And so even if you could discount everything else, you cannot discount short telomeres in cell division. Cells stop dividing when telomeres get short. And one of the things that is a problem in regeneration of the body is stem cell depletion. We want stem cells not to get depleted, and therefore lengthening telomeres gives them more healthy divisions themselves. So this is a technology that's very exciting. It's a technology that's been around for decades. It had been speculated, postulated. Researchers argue about it, and yet there was no human data. So there's really nothing to argue about. Whether it works or doesn't work is completely irrelevant until you get human data. And I'm always surprised at people, being in these long debates as to whether a technology works or not when it hadn't been applied. And so I took that technology to lengthen the telomeres, vastly targeting the stem cell populations and dividing cells. Telomere attrition is one of the hallmarks of aging, so it's something that needs to be addressed. It is, when you lengthen telomeres, it just amazingly targets a bunch of other hallmarks of aging, and we can talk about those. So why would you want to lengthen your telomeres? You want healthy cell division. You want youthful cells, and it does seem to change the profile of the cell. So it may have epigenetic effects on the cell, creating a more youthful cell. It definitely helps revitalize mitochondria, and mitochondria dysfunction is the number one hallmark of aging that we see across every disease of aging. It also helps with some cell communication issues, and it may in fact help with stem cell depletion, and that would be one of our major targets, is make sure that your body doesn't deplete of stem cells, which are your regenerative cells that can differentiate into any type of cells that are needed to repopulate an area of your body when there's damage. And so that sort of regeneration is something that we definitely want to target. And so that is why I took the gene therapy to lengthen telomeres. And to be very clear, the gene therapy is the only known way, assured way to lengthen telomeres right now that we know of. I'm saying that again, there are different genetic ways to lengthen telomeres. All of them have to affect the telomerase gene, thereby lengthening the telomeres. And I'm basically bouncing this against small molecules. So there is no known small molecule that I've ever seen that has research that really reflects that you can lengthen telomeres in any other way. And I'm not a proponent for small molecules because if you have a small molecule that's turning on the H-TERT gene, it's very likely turning on other genes as well. So I think that the gene therapy is the most targeted, best way of actually stimulating telomerase and lengthening telomeres.
How do you lengthen telomerase? Are you, is there a gene that you're turning on and you're
Yeah,
upregulating the expression of it, or how does it work?
Yeah, it's called the H-TERT gene. And what it does is it codes for a protein called telomerase. And the telomerase is actually what the chromosome uses to rebuild the telomere at the end of the chromosome. That's a great question. So telomere, telomerase, and H-TERT, it becomes very, very confusing, I know, but H-TERT is the gene. That means the human telomerase producing gene. The telomerase is the protein that the gene makes. Remember, genes code for proteins, and proteins make you. So it codes for a protein called telomerase, and that lengthens the telomere, which is the cap at the end of the chromosome.
So what did you experience once they put your telomeres on the rack and stretched them out?
Right. So when we did testing, we saw telomere lengthening in my white blood cells. So that's the traditional test. That's the most common test out there. And so we used a traditional third-party testing, and we continue to test those. We can assume that we targeted a lot of the cells in my body, but not all of them, because gene therapy doesn't right today have the ability to target 100% of the cells. But the outcome that we saw that we think that is associated with the telomerase induction is, of course, the lengthened telomeres and the T lymphocytes. I had a reduction in inflammation in my body that was significant after the therapy. It was about a 6-fold decrease from the inflammatory markers before. And I also saw a reduction in triglyceride levels of about 50%. So we would consider that as correlating with better heart health.
Yeah, that's far more than any, cholesterol lowering drug could ever get close to.
Right, and actually doing it in a healthy way. So what we're hoping with gene therapy is, and honestly, if we see the same outcome from 10 patients that we saw in my body, that would be hands down the most powerful drug on the planet. Plus, it would be essentially natural. So it basically hits the aesthetics of what people really like. So instead of taking a small molecule that might damage your liver, hurt your kidneys, and have some off-target effect of maybe lowering some cholesterol levels, but putting you at higher risk for type 2 diabetes and dementia, we'd be talking about just at the cellular level upregulating a gene that already exists in your body that's creating a targeted therapeutic protein with no known negative effects. It's pretty powerful.
Okay. These gene therapies, do they need to act locally or systemically is fine? I mean, what governs whether something needs to act locally or systemically, and can it? How difficult is that a problem in all these
That
therapies?
is a great question, and that is why I mentioned how many cells we can target with telomerase, and that's why I didn't mention a cell targeting issue with the myostatin inhibitor. So with the telomerase-inducing gene therapy, the problem is telomerase the H-TERT gene has a localized effect, meaning it's not really shared outside of the cell, and it only has an effect on the cells that are transfected with the gene therapy, or transduced in the case of the body. So if the gene gets into the cell, it has a beneficial effect on that cell, but it doesn't have one systemically. That's why with the H-TERT gene therapies, they tend to be very expensive because they're created in titrations and doses that are trying to target as many cells in the body as possible. The myostatin inhibitor, on the other hand, has a systemic delivery. So if we target it to cells, the protein is made in those cells, but it's shared out into the bloodstream. So it has a full body effect. Although if you do the myostatin inhibitor and you have it, let's say you had it directly injected to certain muscles, those specific muscles will benefit the most, and then it will have a systemic effect on the rest of the body. But So, you do want to think about targeting. If a person has a particular atrophy in a certain area, you're going to have a better response right where you put the gene itself. There is the new thinking and the new therapies that are coming out that are more systemically given, targeting muscle, skeletal muscle with certain tropisms, so certain vector delivery that is specific to musculoskeletal delivery.
So what's the particular role of BioViva? I mean, there's so much to do, and to do trials and get approval.
Yeah.
One person can't do it all, no matter how much your myostatin's inhibited. So what's the role of BioViva? What projects are you working on?
BioViva we're a bioinformatics company, so we think that the most important thing is gathering data on what works and then getting those therapeutics that actually work in studies into the regulatory system as fast as possible, using the study data as the impetus for accelerating trials in certain areas. The regulatory area has a 94% failure rate of drugs. So even if you know your drug is going to work, but you pick the wrong endpoint, you will fail. So our study partner actually gives us the ability to look at data, know where it works, and put it together in a therapy. But we also have a research arm. So our research and development arm is at Rutgers University. It is for a new vector development that can actually carry, instead of today's most common vector, which can barely carry one gene in a promoter, it can only carry a very small package. Our new vector delivery could carry at least 5 to 10 times that much. So on the research and development side, what we want to do is we want to have 2 gene therapies available in the next 10 years, because this is the slow development of research and development. And one of them that is for non-systemic delivered proteins. So one would be a gene therapy where you have to target most cells in the body, and we would package the gene of choice, the many genes of choice, into that therapy. And the second delivery would be systemically delivered proteins. So it would be, you would, in fact, use a lower dose because you would have a systemic outcome from the therapeutic. So on the research and development side, we are working on the DREAM delivery method for gene therapy. That's one of the reasons why all of this data is important and why we want to look at so many different genes. And then on our side, we're just doing the bioinformatics, looking at biological aging. In November, we should have a repository system online that people can use and bring their multi-omic data. We're hoping to also encourage biohackers to come and put their pre and post data so that, your act of biohacking is not a selfish act. It goes farther than yourself to help a lot of other people. And then what we're doing most importantly there is we are handling our partners' patient data in order to analyze how well those gene therapies work, so we can answer to the regulatory system on addressing moving these advances forward, show where they work, where they don't work, no data hidden, and advancing therapeutics for humans, again, in these more mainstream areas where we might be able to, by treating such a large unmet need, actually create affordable drugs.
What are some of the other therapies, the names and maybe how they act, that gene therapies that are here, perhaps they're in clinical trials or they're very close or they're showing considerable promise in addition to telomerase induction and in addition to myostatin inhibitors?
Well, so other genes that we're looking at is we're looking at PGC1 alpha for obesity, to treat obesity, and we're looking at clotho to treat cardiovascular disease and chronic kidney disease with the hopeful outcome of increased cognition. Also, clotho seems protective against Alzheimer's, so that's things that we're looking at. In the traditional regulatory system right now, there are 4 past gene therapies, all of them coming with an absurd, excruciating price that most people can't afford, and we radically need to change that. And that's one of the problems of looking at orphan diseases that don't have a large population, is payers want to recoup the money that they've spent on research and development and getting a drug to market, and it just turns out to be a very inhumane outcome as far as cost associated with those gene therapies. They're considered a one-time treatment for a cure, so people should know that about gene therapy. This is the benefit. This is essentially the future of getting you off of trying to take a pill every day, things that we're not very good at, trying to, get an injection every 3 months or whatever your therapeutic dose looks like. Gene therapy gives you the ability to, a lifetime therapy. We even those companies, I'm not sure that they know that their therapy will last a lifetime, but they're hoping for 10, at least 20 years, maybe a lifetime. And this is the power of the technology. And I think that putting a really high price tag on that is going to shut people out from the humane use of treating disease. Plus, when you're treating something like biological aging, I mean, seriously, the whole population of the Earth, the whole planet, right now, the World Health Organization said that non-communicable diseases, which are vastly the diseases of aging, kill 70% of the global population. By 2050, it's estimated that aging will be the biggest killer in every country of the world. And this doesn't need a high price tag for those companies to benefit off of, selling technology. This is something that we need to get out cost affordably to patients when the technology is predictable. That'll take some amount of years, but it's a huge savings to countries. Each one of the aging diseases is about $1 trillion cost. And then if you think about curing these childhood diseases, which is my focus, on top of that, you're looking at an extraordinary amount of savings to insurance companies, providers, governments, society at large. There's a lot of money lost taking care of sick people, and the benefits are immense. The benefits can be shared globally rather than to very few companies.
Very good. So what's the best way, well, before that, what are some milestones that you're going to be looking to hit in the next year to 3 years at BioViva?
Oh, yeah. Well, right now we're just diligently working on a HIPAA-compliant, GDPR-compliant bioinformatics site so that we can handle all of this data. We're working towards, patient safety. We're huge advocates on our side to making sure that everything on the integrated health side is running as smoothly as possible, but they're very professional. They know what they're doing, but, we're constantly making sure that safeguards are put in place. We are working on, so that, this year we hope to see 100 patients. Next year we hope to see 1,000 patients come through the integrated health system platform so we can analyze the data on these therapeutic interventions, and we hope that to exponentially shoot up year by year. Again, on the bioinformatics side, we're working with a couple of groups building the front end and the back end of a very secure site for patient data. That's a big benchmark to get over. And in the research and development, we will be waiting for the first outcome of these studies over the next 8 to 10 months. Plus, we'll be building new constructs that will be tested of multi-gene delivery with the same vector. So we're really busy right now. We are really busy in every one of the aspects of this company.
Yeah, there's a tremendous amount going on. Well, very good. Well, what's the best way for people to find out more? Perhaps to read papers or see press releases, get in contact.
Right. So if you want to learn more about BioViva, go to bioviva-science.com. You can learn about what we're doing there. Really sorry about the state of the website. If you know a website developer that's really good, please contact me. We've had a couple of not so great experiences, and we'd really like a good experience with that. We're definitely ready for that. So forgive the site, but enjoy the information. And if you want to learn more about treating aging, do not come to me, do not come to anyone else. Go and read research papers or hire a researcher to read research papers. You're going to be so thrilled. Like really, really do the diligence, and then you'll know why we're so excited. Because, otherwise you're going to end up in a debate with someone and they're going to go, oh, I don't think that'll work. And then you're really just like bringing it down to opinions. Look at the damn science. It's really good.
Well, very good. Well, Elizabeth, thanks for coming back. And, again, I don't envy the amount of work you're going to do, but, it's for an excellent cause. So thank you so much for what you do and for being here.
Yeah, thank you. It's my passion. It's my life. I'd rather work than do anything else. So I am at your service. I am your servant. Please, keep us accountable, ask us questions, keep us diligent, and be excited about the future. And when people want to volunteer and participate, please reach out to us. We're always looking for an extra hand and extra help.
Well, very good. Well, thanks for coming.
Yep, thanks for having me.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.